of this is kind of an annoyance on how our traffic is moving. And we might want to have a better way to do this. Now, this is how the hub works. So let's talk about how a switch works. Because one of the things that we have an issue with is all these collisions. Collisions causes what? When the jam signal goes out, we have to wait for those PCs to do their thing. If collisions are consistently happening, there's always going to be jam messages going out. And this is going to cause us issues. So the word went out that we need something better, right? And still having a hub just send traffic to everyone, which means when it goes into this port, if this is a 24 port hub, it's going to go to all 23 ports. Someone said, well, what if we design a mechanism that allows us to only send communication where it needs to go to? And this is where we have a switch. Imagine that when PC 1 needs to communicate with PC 3, that traffic only goes to PC 3. Now that sounds like a dream, but that's exactly what happens. With this method here, we have the ability to send traffic in, and based on the MAC address that we're sending it to, we're going to forward that data to that particular PC. Now we do this by ports. Now these ports are going to be configured automatically to record the MAC addresses. So when PC 1 sends data in, and everyone's MAC address is going to be 1111, this is going to be 2222, 3333, makes it easier, 4444. When this PC sends data into switch 1, immediately what that switch does, every time that data comes in here, he's going to say, let me look at the source MAC address. Because remember, what did I tell you? We're going to have the source IP, the destination IP, right? And that's going to be my layer 3 information. But then my layer 2 is going to be what? Source MAC and destination MAC. So when PC1 sends its data into that switch is going to say, let me look at the source MAC address. Let me look at this. Oh, the source MAC address is 1111. Let me go and make sure that this is in my table. What table? The MAC address table. Sometimes you hear it called the CAM table, but I call it the MAC address table. And in that MAC address table, we have the MAC and the port number. So we'll say this is port 1, this is port 2, this is port 3, and this is port 4. So when the switch looks at that data that's coming in and says, well, 11's not in my table. Well, let's add it. 1111, that belongs to port number 1. Now, he's trying to send this data to 2222. Well, guess what? 2222 is not in its MAC address table. Everything is based off this MAC address table. So when I'm going to need to send data to 2222, I am going to look at my MAC address table to find out where that needs to be sent. Well, it's not in my table. Well, how do I fix this problem? I got to find out where it's at. So I'm going to send out a broadcast message. Anytime switch gets data coming in and it needs to send a broadcast, it will send a broadcast to every port except the one it came in on. This will happen with broadcast and multicast. So the switch, if he has an unknown MAC address, that's what we call it, an unknown MAC address. It's unknown because we don't know where this MAC address lies. We don't have a clue. So we need to find out. So we're going to send out a broadcast. I'm not going to just drop the information. I'm going to send out a broadcast. So it goes out every port. So PC2 is going to get it, PC3, PC4 is going to get it. But the traffic is really meant for PC2. This message that's going out is saying, hey, this is a broadcast. So then we're going to change this information to be all Fs, send it out. PC2 would get it because it's a broadcast message. He's going to open it up. He's going to see that it's sourced from 1.1. And he's going to look at the source IP address and the destination IP address. And he's going to say, well, that's for me. All right, let me go ahead and take care of that. And when he goes to send information back to PC1, well, guess what happens? He builds his source IP, his destination IP, and then his source MAC and destination MAC. He got the source MAC from himself, which is 2222, and he got the destination back from when the data was sent from PC1, which is 1111. Now this data goes into the switch, and the switch immediately looks at the source and says, wait a minute, 2222 is not in my MAC address table. Let me add it. That's in port 2. And then he says, well, let me look at the destination MAC. 1111. Oh, wait a minute. Let me look at my table. Oh, that is in there. Let me send this data to port 1. And port 1 only. Notice I said port 1 only. So originally 3 and 4 got the broadcast, but once this table is built and the switch knows everyone is on the ports, guess what? Everyone can now communicate with each other, and when PC1 wants to communicate with PC2, it only goes to 2. 3 and 4 will never know what PC1 is sending to PC2. Much better than a hub, wouldn't you say? Now, because of all this, this gives us the ability to lower our bandwidth going to other network cards. So imagine having this PC that I had before, and we were doing my gaming. And I remember I had this, like, you know, this fog of war here, and people couldn't see it. But then all of a sudden, my 100-some guys comes on the screen, and I'm on PC1, and PC2 has this area of the map exposed. So that data only needs to go to PC2. PC3 and 4 hasn't explored this area yet. So to its perspective, it's still, those 100 PCs haven't come out yet. Or those 100 characters haven't come out yet. So now, only PC2 needs to get all that data. It doesn't need to go to all of them. Might be a poor analogy, and I apologize for that, but you get the idea. It's either my 100 guys on a game machine, or it's talking about boring application data. I like to talk about games. Okay? Now, this makes it very powerful, because I know now that I have this ability to send data into this port and get right over to port 2. Now, another interesting thing that a switch provides for me is this thing that's called full duplex. Now, before we talked about half duplex. What does full mean? Imagine having a channel just for transmitting and a channel just for receiving. Imagine that. Isn't that what a telephone's like? Aha. A telephone is like that. Where with the walkie-talkies, you can actually think of the walkie-talkies as, you know, as we had these channels going over to the antenna. You can actually think of these antennas as a single cable. But if I had another cable, here's cable 1, here's cable 2, then both of us could push the button, because anytime he is going to push the button, he's going to be talking on this channel, and be receiving it on this end, and whenever he hits the button, he's going to be transmitting on this channel. Oh, interesting. So instead of having our transmit receive on the same channel, one side is going to be transmitting whenever he pushes the button, and the other side of that channel on his end will be receiving. And vice versa. Well, that's good to know, because now we both can push the button and we can overtalk to each other. So when Kyle is sitting over here talking to Tim, Tim could be saying, hey, Kyle, go ahead and pull the lever. And as he goes to pull the lever, and Kyle says, okay, I'm pulling the lever. In the middle of that, Tim can say, wait, don't do anything. Stop. Even though Kyle has his hand on the button. I would say that's much better, wouldn't you? So switches have this interesting thing called full duplex, which is just like a telephone. You and your girlfriend can be arguing for days on the telephone, back and forth, and you don't have to keep using the word over. So now this PC has the ability to send data and receive data at the same time. Now this is nice, because before, when we had our hub had everyone on this same collision platform. There's PC 1. I'm just going to draw boxes this time. PC 3. PC 4. PC 1 sends data in, which means if PC 3 or 4 or 2 send data at the same time, it collides. Which means 2 can collide with 3, 4, and 1. 1 can collide with 3, 4, and 2. 4 can collide with 2, 3, and 1. Does that make sense? So this hub and all these devices are in one big, what we call a collision domain. We're in one big collision domain because these PCs can collide with each other. And this is a problem. So now, think about our full duplex. Because over here, we can only communicate one at a time. If anyone else is communicating, we're colliding. With a switch, it gives us the ability to have those multiple channels to transfer and to transmit and receive at the same time. So now, guess what? If this data goes into this switch port and does not go to everyone, it only goes to the port that it needs to go to, and it's only forwarded based on the MAC addresses that have been found on those ports, I'm not going to have the ability to collide with 3, 4, or even 2. Oh, this is pretty awesome, because now, how far does my collision domain go here? From the switch to the PC. And you have to ask yourself, where can I really have a collision? Really? Because if I'm transmitting on this channel and receiving on this channel, how will they ever collide? Where in our half duplex, I can transmit and I can transmit, but I'll be doing it on the same channel, and once they meet, boom, they explode or collide. So my collision domain is per port. And that's what makes it wonderful. So what's the key factor of learning about a switch? It uses MAC addresses to do its forwarding decision. It'll also send out broadcast messages if I have them all set to FFs. As my MAC address is my destination MAC address, it will send those out as a broadcast. It goes out all ports except the one it came in on. Also, if I have an unknown destination MAC address, if I have that, that means I have to send out a broadcast. It'll go out, and what does the broadcast do? Again, all ports except the one it came in on. So this is awesome. So what did we learn about a switch? 1, the second the data comes into a switch port, it checks the source. Every time that data comes in, it checks the source MAC address of the layer 2 header. If that information is not in the MAC address table, it puts it in there. Now that's nice to know, because if I take PC off of port 1 and plug it into port 10, what's going to happen? In the MAC address table, it will see that 1111 belongs to port 1. But the second that this PC is plugged into port 10 and starts sending data out, the switch is going to see that MAC address 1111 is coming in on port 10. And what is he going to do immediately? He's going to remove it from 1 of the table and put it in port 10. So this whole entry will be removed with the port 1, and he'll put a new entry in for port 10. Okay, does that make sense? Port 1's entries will be removed, port 10 will be added. And this is constantly happening. So that gives you the ability to plug in devices anytime you want. The switch will do its job. He will record that MAC address. Now, based on the fact that I'm plugged into switch port 10, anytime PC needs to communicate with PC1, that data comes into this switch port. Switch looks at the data coming in on port 3, looks at the source MAC address, says 3333 is not in the table. Let's put it in there on port 3. And let's look at the destination. Destination is 1111. Oh, well, that's already in my table, so I'm just going to forward that data out port 10. No actions needed, just forward it. All based on MAC addresses. And that's the beauty of a switch. And that's the power of the switch. So that's pretty much all our devices, our LAN devices. So let's talk about our distance. How far does a LAN really go? Where does it end? Well, that's pretty interesting. Let's take a look at this. Here's a PC. PC 1. Going into switch 1. We're going to say it's on the 192.168.1.0 network. This is PC 1 here. So here's my network number, here's my network number, here's my network number, and this is a host number. Now, obviously 0 can't be a host, so we'll just turn this into... Now, 0 can't be a host for this particular network. You will be able to see that there's zeros and IP addresses later on. Now, because of this, PC 1 has an IP address and a MAC address. In order for him to communicate with this router also has to have an IP address and a MAC address. Otherwise, it will not be able to communicate. Now, if PC 1 pings PC or router 1, we know what's going to happen. The first thing that's going to happen is he's going to build his layer 3, he's going to build his layer 2, and he's going to send it on. Source IP, destination IP, source MAC, destination MAC. That gets sent out. He gets the MAC address information from himself, the destination MAC address he gets from his ARP table. That hits the switch. Now the switch looks at the source MAC, finds out if it's in the MAC address table, adds it in the MAC address table if it's not there, then looks at the destination MAC address, and then forwards it on based on the MAC address table. Which means if your MAC address table is incorrectly, it will go out the wrong port with no hesitation. So now this data is going out this port, hits the router gets it, and he responds to the ping. And he does the exact same thing PC had to do. He has to build a layer 3, has to build a layer 2, has to look at his ARC table for the destination MAC. Same thing, sending the data back.